kind of an interesting day in front of us, I think. Oh, I sent you all some email, which you may not have caught because I just sent it this morning. I actually have a master's defense to go to, so I will be out of the office from a little bit before 10 till noon today. If this is wrecking your life, then come talk to me after class and we'll set something else up. So, last time we defined what it meant for a non-empty set of automorphisms of a field to be linearly independent. And so that is a non-empty collection of automorphisms. What does it mean for these to be linearly independent? We say that they're linearly independent given any collection. Given alpha I and F, sigma I in this non-empty set of automorphisms, the relation AI sigma I u equals 0 for all u in F implies that AI is 0. So this is kind of reminiscent of what you're used to for like a linear transformation. And so now with this terminology in hand, follow. If you have any family of distinct automorphisms of that, F is when set is linearly independent. Right there. So let's prove this. If not, there exists alpha 1, alpha, or A1 of the AN, sigma 1, so there, sigma 1, sigma n, such that the sum AI sigma IU is 0 for all U and F. So that's what it means for those to be linearly dependent. So there is some collection of n out of our set of distinct automorphisms, which for which this is true. Let's assume that we have chosen a minimal such dependence relation. So there might be many of these dependence relations, right? And I'm going to pick the one that's smallest. And let me point out that, of course, n must be bigger than 1, because, for example, if you have a u, oh, I'm sorry, a sigma u equals 0 for all u and f, then this immediately implies that a is equal to 0, because all you have to do is take u equals 1, and sigma of 1 has to be 1, and so that will mean that A is 0, right? So your n does need to be bigger than 1, right? And of course, maybe you can smell what the rock's cooking here, because what I'm going to do is I'm going to reduce this, right? And that's going to be my contradiction. I want to show that this minimal relation leads to one that's in fact smaller. So, so we know that the automorphisms are all distinct. So distinct, find D and F such that sigma 1 V is not equal to sigma 2. Right, so there must be some element of the field for which sigma 1 and sigma 2 different on. And we apply this equation to UV. So this thing is 0 no matter what I plug in for U. So I'm going to plug in UV. Right. So what we have is A1 sigma 1 U sigma 1 V plus A2 sigma 1 U sigma 2 V plus AN sigma 1 U sigma 2. Right. I'll find this to sigma. And this, as I say, is just this equation right here with U replaced by U. So we've got that here. We also will multiply this equation by which sigma 1b. I'm also going to multiply this equation by sigma 1b. And that gives me A1 sigma 1u sigma 1b plus A2 sigma 2u sigma 1b plus AN sigma NU sigma 1b. That's also equal to 0. Right? And as you might guess right now, what I'm going to do is I'm going to subtract these two. Right? And notice if I subtract these two, the first terms are the same. And everything else, so this is to get A2, let's see, that's going to be sigma 2, well, sigma 2b minus sigma 1b. Sigma 2u. All the way up to AN. Sigma n. Check myself here. Sigma nb minus sigma 1b. Sigma n. Sigma. And notice, remember, we picked these to be 0, right? And so notice that these are now, these differences here are elements of the field, right? Because these are automorphisms, right? So this is A n times some augmented. Notice that this has to hold for every U in F. And now what we have is we have an equation where no matter what I plug in for U, this always works. And it's smaller than the original one, and it's not trivial, right? Because this term right here is not zero. So this contradicts. Minimal. And so this gives our result. So our set of distinct automorphisms is when we're going to use this in kind of a key theorem in just a bit. Let me give you a definition first. We say that F is cyclic. I've given you this, but I'm going to formally write it down. Cyclic, respectively, abelian, extension of K, if F is Galois over K, and the Galois group of F over K is cyclic, or respectively abelian. So the cyclic or abelian modifier refers just to the Galois group. These are actually important. So one of the cool things about abelian is, remember in our correspondence theorem, then the big field is Galois over every intermediate field. But the intermediate fields may not be Galois extensions of the small field. But in abelian extensions, they have to be. Because, why? That's right, because all the subgroups are normal. Exactly. And so abelian extensions are studied a lot by people in number theory because of this property that every intermediate field is Galois over the base field. As you might expect, you get kind of better results. It's a nicer playground to play in. So now with these definitions in hand and this notion of linear independence, it's called theorem. Let F be cyclic over K of degree n. So this is an extension of degree n. It's cyclic. So when I say cyclic, and I'm saying that it's Galois. We'll let sigma, this automorphism, be the generator of the Galois group. And U is in F. Okay. Number one, the trace of mu is 0 if and only if U, this element whose trace is 0, the trace of an element is 0 if and only if that element is of the form of B minus an automorphic image of V, and not just an automorphic image of V, one from the generator. That's kind of cool. Two, as traces to addition, norm is to multiplication. There's an analog of this as well. This is famously called Hilbert's Theorem 90. Man, you got it going on when somebody says Hilbert's Theorem 90, right? I mean, I would love it if at some point in my life that somebody would put up Quakenhill's Theorem 4. I'd settle for a 4, you know, but that's pretty awesome. So, by the way, anybody want to guess what the analog of this is? Right, so how might this translate to the multiplicative situation of the norm?
Would it be V divided by sigma V?
Okay, that's right. And what about the value, right? Trace is 0, so the norm should be 1, right? So additive identity to multiplicative identity. If and only if U is equal to V, sigma V inverse, some V in that. Okay, so this is not super hard once you see how to do this. It just requires a little cleverness. I'm actually going to go through both of them. Kind of show you what goes on here. And once you see the additive, I think it shows you how the multiplicative is going to work. But there's one little caveat, I think, because maybe it's not clear how to translate the additive part into multiplicative. So let's do number 1 first. Actually, let's do that direction for both 1 and 2, because oh, I'm sorry, that's not what I want to fix. I want to start easy. This is what I want to do. Because it's actually fairly easy to show that if these elements happen to have this form here, then their trace is 0, norm is 0 respectively. So if U is V minus sigma V, then the trace is the sum right, because of course all the conjugates that you need are just powers of that sigma, right? So this is and this is and now, yeah, that's right, it's just a shift, isn't it? This is this is actually just a trace of V. And so is this, because it's just, and of course, there's, you know, you're just basically shifting it so you get the same set of conjugates. Or another thing you could do is you could pull a single sigma out of here, and what's left is sigma times a trace of V, but the trace of V is in the base field, and so that's just trace of V.
Should that sum go to n-1?
It should go to n-1, thank you. Yes. Okay, the norm is similar. I'll sketch this more briefly. If Q is the, I'll write it this way. That way, then the norm which is the product I equals one, I equals 0 to n minus one, sigma b, over the product I equals 0 to n minus one of sigma, this should be sigma I, shouldn't it? I plus one as well, which is norm of p over the norm of b. Okay, so that's the easy way. Okay, so if I happen to encounter an element that looks like this, well, in its cyclic extension, of course, the trace must be 0 and same the norm. All right. The interesting part is these conditions are enough to guarantee that that element is of that form. Right. So let's look at the other direction. So let's look at the additive version here. And we're gonna need some of the stuff that we built up. So let's suppose I'm gonna suppress the superscript field here, so forgive me on that. What I'm gonna do first is I'm gonna find an element such that the trace. So step one in our recipe, find W and F such that the trace of W is equal to 1. That's going to be, it looks like I'm just kind of pulling this out of some strange orifice, right? But the truth of the matter is where this proof was born from was somebody's blood, sweat, and tears. So we know that this is coming. How are we going to do this? Right? I mean, how do you know that there's something in trace 1? Well, really, all you need to do is find something that's got trace not 0 and divide out by the trace, right? And so how do you find something whose trace is not 0? Well, the automorphisms are linearly independent. Why? Because they're distinct, right? And that's that thing that proved that you have distinct automorphisms. Of course, it's cyclic, and there you go. So there exists a Z and F such that Z plus sigma Z plus sigma squared Z plus sigma n minus 1 Z is not 0. Right, the linear independence of these automorphisms guarantee that there's some Z which is not 0, and check it out. That's the trace of Z. Right, and so there's your element Z whose trace is not 0. So what we're going to do is we're going to take W D over trace Z. And of course, trace Z is not 0, right? So now that I've sagaciously picked this W that has trace 1, this is gonna simplify the computation that I'm gonna have to do here. So what I'm gonna do is, and this is a setup, this is like, okay, it looks like Jim's up here having a stroke or something like this, but you will see in the second step why this kind of connects up. So I magically wave my magic wand and pull the following element out of my hat. V is equal to UW, where W is that element that we've picked here. Plus U plus sigma U, sigma W, plus U plus sigma U plus sigma squared U, sigma squared W. And you continue this up to the last element in my list is going to be U plus sigma U all the way up to sigma n minus 2 U times sigma n minus 2 W. And this is going to be my V. Okay, everybody kind of see the pattern of what I've done? So that I kind of make this expansion. The W's kind of go up nicely. And I just have bigger and bigger sums of the successive powers of sigma acting on U. And I stop at the n minus 2. Okay, now I apply sigma to this. Add this up. This is sigma U, sigma W, plus sigma U, sigma squared U, sigma squared W, plus sigma U, sigma squared U, sigma cubed U, sigma cubed W, all the way up to sigma U, sigma squared U, sigma n minus 1 U, sigma n minus 1 W. Okay. Is everybody cool with what we did? I want to make sure that I'm not losing. I just applied sigma here and literally use properties of the fact this is an automorphism. Right? Now let's subtract these. This minus this. And I'm here to tell you it's a bloodbath. Well, okay, you're still hanging around, looks like, at least for now. But what happens here, right. Notice that you've got a sigma U, sigma W here, which is canceled by this, right? So that's gone, but I'm left with the first factor here, right? So what's left over is U sigma W. Everybody okay with that? What happens here, I've got a sigma U, sigma squared U, sigma, all times sigma squared W. That's this thing right here, right? So this minus this gone, leaving only the U times this, right? This pattern continues. Okay. We just need to kind of figure out what happens sort of at the end game. And the last bit that is not subtracted off is this. Sigma U sigma squared, sigma cubed, U sigma n minus 2 W that's this bit canceling with the hidden one here. And the last bit is, and I'll write this out loudly. Actually, my bad, because this is what we're being subtracted from minus. Now, anybody know the next step? I claim that this mess here is minus u. Right? And that's because the trace of u is 0. This is because u plus sigma u plus sigma n minus 1 u is equal to 0. So this mess here should be negative u. So what we have is E minus sigma B is U W plus U sigma W plus U sigma squared W plus U sigma N minus 1. And this is U times W plus sigma W plus sigma N minus 1 W, which is U trace W. That's why it was convenient for the trace of W to be 1. So B minus sigma B is equal to U. And we have our desired result. Okay. And of course, you see that the cyclic, it's kind of a setup, right? You get this big cancellation. There's something similar for Hilbert's theorem 90. Let's give that one a whirl. So now we suppose that the norm of u is equal to 1. And in this case, I wanted to go through this one as well, because I think making the jump here, like finding the elements, the important thing here. So we find y in f such that d is uy plus u sigma y plus u sigma squared u plus u sigma u all the way to sigma n minus 1 u sigma n minus 1 y is not 0. So pick, this is kind of similar to finding the trace of w to be not, or to be 1. How do I know I can do this? Well, this is again kind of a linear independence automorphism thing, because let me kind of put this parentheses. U sigma squared u sigma squared y. U sigma sigma n minus one u, sigma n minus one y. And so, notice that there must be some y for which this is not zero. There exists y such that v is not zero by linear independence of the automorphisms, one sigma of the sigma n minus one. Right, so it's the same kind of business that we had going on last time. Okay, so we make such a choice. That is, we assume that this v in this form is of that form that is not zero. So notice, so if you notice here, u sigma u sigma n minus two, u sigma n minus two y, u sigma u sigma n minus one u sigma n minus one y. Now let me observe that the last term, by the way, can somebody tell me there's kind of a alias for this?
Coefficient is the normal.
That's right, the coefficient is the norm of u, which is one, so this is actually sigma n minus one y. Right, and that's where we're using the fact that the norm of u is one. So let's hit this with well, so let me do a couple of comparisons here. Let's look first at sigma v. Sigma u, sigma y, plus sigma u, sigma squared u, sigma squared y. Plus sigma u, sigma squared u, sigma cubed u, sigma cubed y. So notice just like before, this kind of kicks it one step further. Sigma u, sigma squared u, sigma n minus one u, sigma n minus one y, plus sigma u, sigma squared u, sigma n u, which is u, sigma n y, which is y. Do I agree with that? Because when I do this, the sigma n here is just, that's the identity automorphism, because remember this is cyclic for n. And again, sigma n y is just y, this is the identity. Everybody okay with that? Yes.
Oh, I mean, we observed that the last term is sigma n minus one y. So that should just be sigma n, which is y.
So, yeah, so this last term should be, I guess, at the end of the day, this should be, yeah, that just should be y. And this, of course, is,
Still the norm.
that's right. So you can go full circle on that, can't you, right? That's y. So this is what sigma v looks like. And I want to also look at what u inverse v looks like. just apply U inverse. I get y plus sigma u, sigma y, plus sigma u, sigma squared u, sigma squared y, plus sigma u, sigma n minus two u, sigma n minus two y, plus, U inverse everybody okay with that? I think I did that right. U inverse kills the U everywhere. And of course, oh well, if you like, we can look at it this way. It's also some puzzle looks. Another way to look at this is sigma U, sigma n minus one U, sigma n minus one y, right? But this is the same thing as U inverse times sigma n minus one, because notice the product of this is the inverse of U, again, because the norm is, of U is one. Now let's compare these. See, notice these things right here are just, all these things with the U stripped off, right? Right, and this compares to the next thing, which isn't there. These all compare up. And who's left out? Well, let's see, where's my Y here? Oh, yeah, and I forgot. Let's see.
That's great.
Yeah, the Y's up front there, so this Y. Wrong one. No, that's right. This Y compares here. And so what do we have? Sigma 3 is U inverse V, and so U is V over C. And then- Okay, any questions on that? Okay, so I'm gonna actually give you what I think is kind of a groovy little application of this. And some of you, let's see, I guess, well, at least you have that. I guess you both had the class about the factorization technique. So we've seen this from another point of view, but here's kind of a neat example of a number of examples. Here's an example of Hilbert's theorem 90 in action. So consider Q inside QI. This is cyclic. The Galois group is complex conjugation. So we've got two automorphisms here, and actually maybe just I should call that sigma or something, make it a little better. Now, kind of something that comes out of this, I'll call this sigma. So let's apply Hilbert's theorem 90 to this particular situation. So let's suppose that A, B, and the rationals such that norm of A plus BI is equal to 1. Okay, so suppose we've got that. So in this situation, this means that, right, because the norm of this is A plus BI times A minus BI, which is A squared plus B squared. So in other words, so suppose I have A and B, so this is the norm of A plus B, A equals 1. So these are, this is a rational point on a unit circle. You can think of it that way. Now, according to Hilbert, theorem 90, there exists a Z there exists Z in QI such that A plus BI is Z over sigma Z. Agreed? And so this is if if Z is X plus IY, then what this means is A plus BI has to be able to form some X plus IY over X minus IY, right? And so we can rationalize this and of course, if this sits on the unit circle, that denominator can't be 0. And this is going to be X squared minus Y squared plus I times 2XY. Right? That's what you get there. Everybody okay so far? So this gives equating real and complex parts. What you get is A is equal to and B is equal to 2XY over X squared plus Y squared, right? And actually, you can take X and Y to be in the integers, because if they're fractions, you can just rationalize them both the same way, right? If you can assume they're over the same denominator, just kill that denominator, and you've got the same fraction. And so basically, this gives the parameterization of rational points on the curve, right? The A part can be this, and the B part can be this. This gives you the famous parameterization of Pythagorean triples, right? So we get all that from Hilbert's theorem 90, for example. Okay, any questions? That's kind of a nifty example. We will finish up next time. We'll talk about cyclotomic fields, and then probably push on to maybe some different territory. Any questions? All right. Well, you all have a good one, and we will see you on Friday.